Yeah, you can start now.
Okay, okay. Okay, good evening. I am trying to do this with a new device that I have acquired recently. So I will. So it will take some time because I am getting used to this.
Sir, which application is this?
This is same, but I I have got an iPad. So I am trying
Oh,
to
okay.
use iPad. So here
Yes, sir.
I will see it. I can write it and see it also. So that is
Oh,
like
oh,
writing it on a paper like that.
oh, it is not action at a distance.
It's not. It's not a domain codomain problem. Is not there in this.
Oh, they're nice. Sir, what about writing comfortability? Means,
Yeah. So I'm. This is my first class with this.
oh, okay,
So
sir.
I hope we will know by the end of this class.
Yes, sir. Yes, sir.
So the screen is not yet come, right? Or has
Yes,
it
sir. Yes,
come?
sir. Just now it came, sir.
Okay. Okay. So you can see the notebook. My notebook.
Yes, sir.
Okay. Okay. So this is session 14, 17, I think, right? Okay. So today, let's try to understand understand some issues about angular momentum. Are you able to read it, or is it too small?
It's
Can you
okay,
read?
sir. Yes, sir. We can read, sir. We can read, sir.
Okay, okay. So classically, we know that angular momentum can be written as L vector. How do we define this? An R vector and a P vector, a cross product of R cross P. And if you can write down now in quantum mechanics, this is in classical mechanics. In quantum mechanics, what happens is that Lx, Ly, and Lz, they become operators. What kind of operators are they? Because we know R cross P, so you could write a determinant form like this for R vector. So R is X, Y, Z, and P is Px, Py, Pz, and then take the determinant to get your L. So you can say that Lx operator is equal to Y operator into Pz operator minus Z operator into Py operator. Like this, you can write down for Ly and Lz also. And we know that commutator of X with Px or Y with Py, Z with Pz. is equal to IH cross. Any other commutators are all zeros. For example, commutator of X with PY. X operator with PY operator is 0. And so on. Except these three commutators, all other commutators are 0. Now use these commutator identities. Suppose if you have A, B plus C, that is equal to AB plus commutator AC. Now this can also be like this: A plus B commutator with C, that is equal to AC plus BC. Further, if you have commutator A with BC, this is equal to AB commutator into C plus B times AC commutator. Okay. Similarly, if you have AB comma C, this is equal to A times BC plus AC times B. Now, so let us call this as equation 1 and these many things as equation 2. So using 1 and 2, 2 means these identities, okay, these identities plus this ZP, ZY, PY, XPX commutators. We can show that LX operator, LY operator, the commutator of this one will be IH cross LZ operator. And then cyclic. When I write cyclic, what do I mean? Imagine we have LX here, LY here, and LZ here. So when you have a commutator of LX, LY, it will be equal to IH cross LZ. Now LY, LZ, it will be commutator of LY, LZ is LX. Now LZ, LX is LY, like this. But if you come in the reverse direction, okay, this is the direction in which if you say LX, LZ, then that will be minus IH cross LY. Okay, is that clear? So this is something I'm not going to show, but you can show this using these identities and then those basic commutators of XPY, XPX, YPY, ZPX, ZPZ, you can show this. Now this can be written in a compact notation. So in compact notation, we can write it like this. So let us say Li comma Lj, the commutator of Li Lj is equal to, okay, so maybe I should use Lj Lk. So let me write like this. Lj Lk is equal to IH cross and epsilon J K JK, let us say some M into LM. So this is one way of writing, where this epsilon ijk is what is called a Levis-Civita symbol, Levis-Civita tensor. It's a third rank tensor. Okay, so epsilon jkm is called Levi-Civita tensor. If you don't know what this tensor is, it's very simple. This epsilon jkm is equal to 1 if this jkm is equal to 123 or 312 or 231. That means these are like cyclic permutations. This is equal to -1 if this jkm is equal to 213, 321, 132. Among these 6, all the 6 permutations are completed, and it is 0 if any 2 indices are same. Okay, so this is how the definition. So this will have in general, since it is a rank 3 tensor, it will have 27 components. Now, among these 27 components, only 6 of them are non-zero, 3 of them are +1, and 3 of them are -1. So now here, now this jkm. So j is equal to 1 for x coordinate, or j is equal to 2, j or k or anything, any index for y coordinate, and j is equal to 3 for z coordinate. That is the change in the notation. Okay, so now you can ask what is L1 comma L2. That means it is Lx comma Ly. That is equal to IH cross. Now 1 and 2 are fixed, so we have epsilon 1, 2, and some m is here, and Lm. Now what is m? If m is 1 or 2, then it will be 0, right? So only when m equal to 3 is what survives. So that is equal to IH cross L3. That is Lz. So this is a compact notation. So what is the notation? In this notation, this commutator relation is written as Lj comma Lk commutator is given by IH cross epsilon jkm to Lm. So this is the commutation relations satisfied by the angular momentum. Now there is another notation which you can write it. So another notation. Suppose if I have an L operator, a vector operator L, and then the take cross product of the same vector operator. What do we get? The L cross L. If I take, what do we get? What is the cross product of a vector with itself in general?
0.
0, right? So, but here it is not 0. Okay, so you can write this as IH cross L. L cross L is equal to not 0, but this is equal to IH cross L. Now, how do we understand this? So my claim is I'm going to claim that whatever I have written here, this and this are same. They both are same. This is even compact way of representing the same thing. Okay. Now, why this is not 0? Because these are not simply vectors, but these are vector operators. Okay. So, if you say L cross L, okay, now you have to understand that this L cross L is going to be something like, so let me just show that if you have I cap, J cap, K cap, L1, L2, L3, now L1, L2, L3. So let's say you have some, this is for L cross L, right? So what is the first component? That is L cross L of first component. That is equal to L2, L3 minus L3, L2. Correct? Now, if they are not operators, then they are zeros because L2, L3 and L3, L2 same. But since they are operators, this is equal to commutator of L2, L3. But what is commutator of L2, L3? That is equal to IH cross L1. So what is that we are finding? L1, L cross L1 is IH cross L1. Now, similarly, if we take L cross L of 2, it will be IH cross L2 and so on. That is how this identity, this L cross L is equal to IH cross L, is same as all these commutation relations. Okay. So that is what is the difference with respect to the angular, the operator cross product with operators, because operators don't commute, so the value is going to be the commutator. Okay, fine. Now we have these commutation relations. Now we would like to solve an angular momentum problem. Okay, so you can see that you have three components of the angular momentum: L1, L2, L3. Okay, so these are components of angular momentum. And they don't commute amongst themselves. And the commutation relation is given by this Lj, Lk is equal to IH cross epsilon Ij, Jk, M, Lm. Okay. Then we can define an operator called L square, which is equal to L1 square plus L2 square plus L3 square. Now we can show, I will also leave this commutator as an exercise, show that L square with Lj is equal to 0 for all j 1, 2. That means L square commutes with all its components. Okay. Now, angular momentum problem. angular momentum states are, you take two vectors that commute and then look for their common eigenstates. Common eigenstates of L square and L3. You can take L square and L1 or L square and L2 or L square and L3, but normally we try to take L square and L3. Okay, why we take like that we can see later, but we will understand later. But let's say that we will take L square and L3. Okay. Now let's say that we start with, it's a common eigenstate, right? Common eigenstate means there will be one quantum number associated with L square and another quantum number associated with L3. Okay. So denote a quantum state which I can write it as alpha comma beta as a common eigenstate of L square and L square and L, such that when L square is operating on alpha, you will get h bar square into alpha. Sorry, I must write it as L square is operating on alpha comma beta. H bar square alpha into alpha comma beta. Why I am writing h bar square? When there is an operator with square, there will be h bar square. If there is only one operator, linear thing here, not L square but L, then it will be only h bar. So in the next, if I have an L3 operator acting on alpha and beta, this will be h bar beta into alpha beta. Why h bar here? Because L3 to the power 1 here. Here L square here. So whatever is the power here, that power will, that means every operator in quantum mechanics will be of the order of h bar. And hence when you say you have L square will be proportional to h bar square, L3 will be proportional to h bar. So I am factoring that h bar out. Remaining is alpha and beta. Now at this moment you remember that this alpha and beta are to be determined. We do not know yet. Okay. So I have used L3 already. Since L3 and L square are commuting with each other, I am trying to find out eigenstates that are common to both L square and L3. Now let us define some new operators using the other two components that I have not used. So I'm going to define L plus as L1. L plus is an operator. L1 plus I times L2. And then I define L minus as L1 minus I times L2. L1 plus I times L2. So I will write these two equations in a single equation like this most of the times. So L plus minus is equal to L1 plus minus I times L2. So this one equation is basically representing both these equations. So like whenever plus is there, you read with this plus, top one with the top one, bottom one with the bottom one. Okay, so this contains actually two equations. Now using angular momentum commutation relations, what are the relations that we have? We have L1 comma L2 commutator is equal to IH cross L3. Then L2 comma L3 is equal to IH cross L1, and L3 comma L1 commutator is equal to IH cross L2. And if I have reverse, for example, L2 comma L1 will be minus of this. That's all, right? So these are the three angular momentum relations that we have. Now using these relations, we can try to find some results like this. For example, let's say that I'm interested in asking what is the commutator. So what is the commutator? L plus and L3. What is the commutator of L plus and L3? So that is L1 plus I times L2 with L3. So using one of those identities that I have said, this can be written as L1 comma L3 plus I times L2 comma L3. So what is L1 comma L3? L1 comma L3 is L3 comma L1 is IH cross L2, as you can see here. Now L1 comma L3 is minus IH cross L2 plus I times L2 comma L3 is IH cross L1. So I and I becomes minus 1 here, or you pull out a H cross. So that is, if I pull out a H cross, so this becomes a minus H cross, then this becomes L1 plus I times L2. Correct? There is a correct. So I will write it in the following way. So let us write this commutator. I evaluated the commutator L plus comma L3, but I will write it as L3 comma L plus. Then what happens? It is negative of this, right? This is H cross L. Fine. So that is our result. Now I will leave this as an exercise. Okay, show that L3 comma L minus is equal to minus H cross L minus. So these two equations we can write it in a combined. That is why I have, so commutator of L3 comma L plus minus is equal to plus minus H cross L plus minus. Okay, so this equation also is two equations. Upper sign means upper sign, lower sign means lower sign. Okay, so this is something which we have evaluated. Then we can also see that it's not very difficult to note this. Note that the L square operator will commute with L plus minus operator. This is obvious because it commutes with L1, it commutes with L2, it commutes with L3, and L plus minus are made up of L1 and L2. So it commutes with L plus and L minus also. Okay. So these are the results that we have. Fine. Now what we want to ask is, we want to ask the following question. So we have to characterize, we have to find the state alpha comma beta. Right? We have just labeled it as alpha comma beta, but we have to find this. What is it that we know so far? We know so far that this is a common eigenstate of L square, alpha comma beta, with an eigenvalue h bar square into alpha, alpha beta, and it's also an eigenstate of L3, alpha beta, which is equal to h bar beta times alpha beta. So in order to get more information about the state, we ask the following question. So we ask a question, what is the action of L plus operator on alpha comma beta? This is the question that we are asking. So that means we start with L plus acting on alpha comma beta. At this moment, we don't know what this is. Okay, but in general, any operator acting on a state will change that state. Let us say that the resulting state of the operation of L plus and alpha beta, let me call it as some phi. Okay, why I am writing like this? In general, operator maps state alpha comma beta to another state. We call it phi. Okay. But now we are going to ask the question, what is this phi? So the next question is phi an eigenstate? Is phi an eigenstate of L? So that is the next question that we are asking. For that, what we should do? We should operate L3 on phi and see. So let's operate L3 on phi. But what is phi? Phi is nothing but L3, L plus operating on alpha comma beta. We don't know what is the action of L plus acting on alpha comma beta, but we know what is the action of L3 acting on alpha comma beta, right? So let us go back to this commutation relation. So notice that since the commutator of L3 comma L plus is equal to h bar L plus, we can write L3 L plus minus L plus L3 is equal to h bar L. That is the meaning of commutator. So this gives you, instead of L3 L plus, I could write this as H cross L plus L plus L3. If I take this term to the right, I will have this. Now here in this particular equation, I have L3 L plus. I have L3 L plus. I replace it with this. So what am I getting? I'm getting L3 acting on phi is equal to H bar L plus L plus L3 acting on alpha beta. What is L3 acting on alpha beta? L3 acting on alpha beta is H bar beta into alpha beta. So this is H bar L plus acting on alpha beta plus H bar beta L plus acting on alpha beta. So that is equal to H bar into beta plus 1 L plus acting on alpha beta, or in other words, this is H bar beta plus 1 phi. What is it that we have found? What is the answer? The answer is phi is an eigenstate of L with eigenvalue H bar beta plus 1. Okay, so this is what we have found. Now you can say that we can write it. It is L plus acting on alpha comma beta is equal to, we don't know, there can be some constant which I will call it as C plus. This is alpha, but instead of beta, you should have beta plus 1. If we have that one, then L3 acting on this one will be H bar beta plus 1 into the same thing. So this is a constant which we have to determine, but then this is the action of. So the quantum number associated with beta, L3 will get incremented when you operate L plus on that. Okay. In the same way, we can also show, by applying L minus on alpha comma beta, that L minus acting on alpha comma beta is equal to some constant C minus times alpha beta minus. This will actually lower the quantum number associated with, decrease the quantum number associated with L3. So since this is like increasing the quantum number and this is decreasing the quantum number, these operators, this L plus L minus operators, are called ladder operators. Or they have another name, raising and lowering operators. Which is rising? L plus is a rising operator and L minus is a lowering operator. Okay. Now, let us look at another interesting operator. Suppose you take, so consider an operator given by L1 square plus L2 square. Because L1 square plus L2 square is a positive operator. Note that it is a positive operator. What is the meaning of positive operator? Meaning of positive operator is the expectation value of this operator L1 square plus L2 square is always positive for any psi. For any psi, the expectation value is positive. Such operators are called positive operators. So in particular, let's consider the expectation value of this operator with this particular state alpha beta. L1 square plus L2 square. With this state alpha beta. Now, this also should be greater than or equal to 0 because for any state it is greater than or equal to 0. So for this state also it should be greater than or equal to 0. Now, note that since L square is equal to L1 square plus L2 square plus L3 square, we can write L1 square plus L2 square to be equal to L square minus L3 square. Correct? So then this equation becomes alpha beta L square minus L3 square alpha beta. It should be greater than or equal to 0. But remember, this is an eigenstate of L square. This is also an eigenstate of L3 square. So that means what? That means this is h bar square alpha minus h bar square beta square to alpha beta, which is 1, because we are looking for a normalized state. So this gives you that, so this implies alpha or the beta square must be less than or equal to alpha. Beta square must be less than or equal to alpha. That means beta, from here what we are trying to understand is that beta has a lower as well as upper. Upper bound. Okay, beta has a lower as well as upper bound. Okay, so suppose if beta square is equal to alpha, then beta should be square root of plus minus alpha, right? So minus root alpha is one lower bound and plus root alpha is an upper bound. Okay, so that is what is the result that we are getting. It has a lower bound, then it has an upper bound. Okay, So now what happens? So let us say, let beta minimum, beta min and beta max, let beta min and beta max to be lower and upper bounds on beta respectively. Okay, so let beta min and beta max be lower and upper bounds on beta respectively. Okay, now, so we have some beta, and the existence of lower bound means what? Once you reach beta min, then there is no state below that beta value. Okay, so that means what? That means the state alpha comma beta min, alpha comma beta min should be such that it cannot be lowered any further. So mathematically, how do we write it? We say that we have L plus alpha comma beta min should be equal to 0. Alpha comma beta min should be equal to 0. And what does that mean? That means this is some state which is 0, okay? This is some state which is 0. So suppose if I take an adjoint of this state, okay? So adjoint of this state is that alpha comma beta min into L plus, because it will be the adjoint means it will be L minus adjoint is L plus. So this also will be equal to 0. Correct? Okay, so maybe I should probably write it differently. So let me give this argument. So this is anyway equal to 0. That means if I operate L plus L minus alpha comma beta min, that is also equal to 0, right? Because this is anyway 0. L minus is killing this state, and L plus is, if you operate L plus on that, you will not get anything. But now we ask a question, what is L plus L minus? L plus L minus is equal to L1 plus IL2 into L1 minus IL2. So that is equal to L1 square plus L2 square plus I times L2 L1 minus L1 L2. So that is L2 L1 commutator. So that is equal to this L1 square plus L3 square, I can write as L square minus L3 square, just like in the previous case, plus I times, we have minus IH cross L3 from the commutation relations. So that is equal to L square minus L3 square plus H bar L3. Okay, so now I substitute that. That implies L square minus L3 square plus H bar L3 acting on alpha beta min is equal to 0. Now L square is operating on this, L3 square, L3, this is an eigenstate of all these operators. So then what do we get? H bar square into alpha minus H bar square into beta square, beta min square, plus H bar square into beta min is equal to 0. So pull out H bar square. So you will get, if you take this to the other side, you will get alpha is equal to beta min into beta min minus 1. So this is the result that I will get if I use this lower bound. Fine. Now we can ask a question that what happens if there's also an upper bound, right? So what did we start? So we said the state alpha beta min. Now we can say the state alpha beta max, okay, is defined by saying L plus, it cannot be raised further. So L plus beta max is equal to 0. So it cannot be raised any further. Okay. Now you do this exercise. Okay, if you do this exercise, we can show that. So repeating similar exercise, similar calculation by operating L minus on the above equation, we can show, we get, I will leave it for you the calculation, alpha is equal to beta max to beta max plus 1. So this is what we will get if we use upper bound. So from lower bound we are getting this, from upper bound we are getting this, but you can see this is equal to alpha. This is equal to alpha. What does that mean? That means whatever is your beta max and beta min, okay, so we get the following relation, that is beta max times beta max plus 1 should be equal to beta min times beta min minus 1. So this is the relation that we will get. Okay. Now from here, what can we say about beta max and beta min? So take everything on one side. So I have beta max the square plus beta max minus beta min the square plus beta min. That is equal to 0. So I can write this as beta max square minus beta min square plus beta max plus beta min is equal to 0. Or I could write this as beta max plus beta min. If I pull this factor out, I get beta max minus beta min plus 1 is equal to 0. Okay. Now, so one result is that either this is 0 or this is 0. Okay. Now you can see if this is 0, what happens? Beta max is equal to beta min minus 1. But that is not possible because beta min is the lower bound. Beta min minus 1 is less than beta min. It cannot be equal to beta max. Correct? So this is non-zero, definitely. This is not equal to 0. So what is remaining? To satisfy this equation, this has to be equal to 0. That implies your beta min is actually equal to minus beta max. Okay, so beta min is equal to minus beta max. So this is the result. So whatever is your beta max, the minimum beta will be minus of the maximum. The lower bound is minus of the upper bound. That means it is symmetric on either side. So this is what is the result so far. Now you can see that. So now we know that. So let us say that you start with alpha comma beta. Start with the states, lowest state, and then apply L plus on this alpha comma beta min. Then what happens? The state goes to alpha comma beta min plus 1. Again apply L plus or L plus square. Then you will get alpha comma beta min plus 2. Go on doing this. There will be some integer, some integer n, such that this alpha beta min plus n. Okay, and this is the maximum. Okay, so that means there exists an integer, okay, basically positive integer, such that L plus acting on n and alpha times beta min is equal to alpha beta max. What does that mean? That means beta max is equal to beta min plus n. Okay, so this n is some positive integer. This n is some positive integer. So that means what? That means your beta max minus beta min, beta max minus beta min is equal to n. Okay. But we know already what is beta min. Beta min is minus beta max. So that means since beta min is equal to minus beta max, we can immediately write from here that 2 times beta max is equal to n. Or in other words, beta max has to be equal to n by 2. N is any positive integer, right? So n is any positive integer. So that means your beta max is going to be n by 2. What does that mean? That means it can be 0, n can be 0, or n can be 1, in which case it can be 1 by 2, or n can be 2, in which case it is 1, n can be 3, 3 by 2. So you can see that this beta max can take values, beta max can take values 0, 1 by 2, 1, 3 by 2, 2, 5 by 2, and so on. So you can see that these are either positive integers or half integers. What are half integers? 1 by 2, 3 by 2, 5 by 2, like that. Okay, if even number is there in the numerator, then that will become a integer. It's not a fractional number, but it's an integer. Otherwise, it is a half integer. See, other fractional numbers are not there. For example, 1 by 3, 1 by 5, 5 by 6, those kind of fractions are not there. Either it is half integer or integers. Okay, so this is an important this thing. So you can say that okay, now you can look at our results carefully. So we have alpha. Okay, so let us know what do I say? I will say that. So let me call beta max to be some L, okay, which is equal to, so this is L. This L can be taking values 0, 1 by 2, 1, 3 by 2, etc. You can take any values like this. Now, if this is L, then your alpha we have seen in terms of beta max, it is beta max into beta max plus 1. Right? That is what we have seen for alpha. That means what? That means alpha is equal to L into L plus 1. Alpha value is equal to L into L plus 1. So, and this is beta max equal to L is the maximum value. And what is the minimum value? Minus L. And in between, it is minus L2 plus L, including that 0. Minus L plus 1, L minus 1, L minus 2, like that it will go from up to minus L. So, relabel our state like this. Relabel the state as alpha comma beta. We will relabel it as L comma M. L comma M. Okay, such that such that L square is acting on L comma M is equal to H bar square into L plus 1 into L. And L3 acting on L comma M is equal to H bar M into L comma M. Okay. And what is the M can take values from minus L to plus L. So that the maximum value of the M is plus L and minimum value of M is minus L. So maximum of M is plus L and minimum of M is minus L. So M goes from minus L to plus L. That is the change. Now what happens to L plus acting on this? Okay, so what is that L plus acting on L comma M? That is equal to some constant which I said C plus, and L and M becomes M plus. So I can say L plus minus acting some constant C plus minus and L M plus minus 1. Okay, good. Now we have to find out this this constant. Okay, so we have to find C plus minus. To complete this calculation, we have to find C plus minus. Now that is simple. So let us first look at C plus. So L plus acting on L comma M is equal to C plus acting on L comma C plus times M plus 1. Now take the adjoint of this equation. Adjoint equation is the ket vector becomes bra vector, L plus becomes L minus, that is equal to L M plus 1, and then the C plus becomes C plus star. So that implies this LM. Now let's say that I will try to take an inner product of these two equations. So I have L minus L plus L comma M is equal to C plus mod square into L M plus 1 L M plus 1. So this is the same state. So this state, inner product of this state is equal to 1. But L minus L plus, okay, is something which we have not. Yeah. So L plus L minus we have seen. So L minus L plus, if you see, so maybe we'll evaluate that here. So L minus L plus is equal to L1 minus IL2 into L1 plus IL2. So that is equal to L1 square plus L2 square plus I times the commutator of L1 comma L2. So that is equal to L square minus L3 square minus H bar L3. That is what this is. That means now C plus modulus square is equal to LM. Here I have L square minus L3 square minus H bar L3. But LM is an eigenstate of L3 and L square. So this gives you H bar square to L into L plus 1. That is for L square minus M square minus M, and this H bar square is common. So this you can write it as H bar square into L plus 1 minus M into M plus 1 minus M into M plus 1. So what will be your C plus? C plus is H bar into square root of L into L plus 1 minus M into M plus. So we have determined this one. Now if you want to determine C minus, what will you get? You will get here L plus L minus. Now L plus L minus we have already demonstrated. Okay, so for that what you get a minus here and a minus sign here. That's all. You get a minus sign here and minus sign there. Okay, so now what we have this result L plus minus acting on L comma M is equal to H bar square root of L into L plus 1 minus M into M plus minus 1 L M plus minus 1. So this is the result of the raising and lowering operators on the angular momentum states. Okay, so if we so let me just summarize what we have done here. Okay, so let me just reiterate. These are the commutation relations that we know, and these are the identities of the commutators. Using them, the first exercise I have given is to show the commutation relations of this Lx, Ly equal to Lz like that. So this can be written in a compact notation. One way to write this is using Lewis-Civita symbol. The other way is to write them as a cross product. The cross product of two operators, even though it is the same vector operator, is not zero because the components don't commute, and hence L cross L is IH cross L. So we start with this commutation relations, and then in order to understand angular momentum states, we consider common eigenstates of these two operators. These two operators commute among themselves, and we look common eigenstates of these two operators. So we denote a state called alpha and beta as a common eigenstate of these two operators, and then show that define L square has an eigenvalue H bar square alpha. Why H bar square? Because here the operator has square, here H bar square, and L3 has an eigenvalue H bar beta. L1 and L2 are not used, so we define two operators L plus minus as L1 plus minus IL2. Now using these commutation relations, you can show that L plus minus, L3 L plus minus is plus minus H cross L plus minus. So this is one result which we have obtained from this. And also note that L square commutes with this. Now we have to find this alpha and beta. For that, what we first do is we will ask what is the result of L plus acting on this. And then notice that this L plus will actually increase beta by 1. So L plus acting on alpha beta is some constant alpha beta plus 1. Similarly, L minus acting on beta it reduces beta. And that is why these are called ladder operators or raising and lowering operators. Then we consider a positive operator called L1 square plus L2 square. By definition, positive operators should have a positive expectation value with respect to any state. So in particular, we take this state, it should be positive for that state also. But L1 square plus L3 square can be written as L square minus L3 square. If we use that, we get a relation like this, which tells you that this beta is both bounded above and below. So the respective lower and upper bounds, we call them as beta min and beta max. And then we consider the lowest state, that is alpha beta min. It should be such that it cannot be lowered any further, which means L minus should make this 0. If L minus is making this 0, then L plus acting on that also should remain 0. So that gives us a relation between alpha and beta min, and that is the relation that we have here. Similarly, for beta max, L plus should make it 0, and using the same type of calculation, we get a relation between alpha and beta max. Now, from these two equations, we equate right-hand sides, and that will give us a relation between beta and min and beta max, and that relation is simply beta min is minus beta max. And then we notice that if you start with beta min and then go on applying L plus, after applying it n times, we will reach beta max. Then that beta max minus beta min has to be equal to that integer, positive integer n. But since we know beta min is equal to minus beta max, we get a result that beta max has to be some integer by 2. So that means it can be either positive integer or it can be half integer. And we call that as L, and then relabel the states alpha beta as Lm, such that L square is acting on that is h bar square into L plus 1, and L3 acting on that is h bar m. Maximum value of m is plus L and minimum is minus L. Now L plus minus acting on them is raising and lowering m, and to find out this C plus minus, we use this L plus and then take the adjoint and take an inner product, and then from that we get this result that C plus minus is equal to h bar square root of L into L plus 1 minus m into m plus 1. So this is what is the theory of angular momentum states, but there are some intricacies or some subtle issues, but we will discuss that in the next class. So I will stop here, and if you have any questions, you can ask. Hello?
Hello, sir. Can you hear me?
Can you hear me now?
Yes, sir, we can hear you, sir.
Okay, so if there are no questions, then we can stop.
Sir, I have a doubt.
Yeah.
Sir, actually, we have defined an operator L square. Is there any actually physical significance actually corresponding to that? Actually, if we have Lx, Ly, Z, we are actually measuring the angular momentum in X, Y, Z direction. So similarly, do we have any physical correspondence to that operator L square?
L square operator.
Yes, sir. L square operator. Yeah.
So in quantum mechanics, what we do is if we have see L operator as so the best thing is to talk about L operator, right? So, but L operator is a vector operator. That means it has components, and these components don't commute with each other. Correct? So when you say L square operator, and if you find out eigenvalue of L square, then if you are asking what is the angular momentum, so you find out for L square and then take the square root of that one. So that is what corresponds to angular momentum, because the magnitude of L, how do you write? You write it as square root of L1 square plus L2 square plus L3 square, right? So from that, this motivation to consider an L square is coming. Correct?
Okay, sir.
Sir?
Yeah.
Sir, Sir,
I can't hear you. I can't hear you.
The maximum can be L square, small L square. Sir, can you hear me?
Yeah.
Sir?
Yeah,
hello,
now
sir?
I am hearing.
Hello?
Sir? Yeah, now I can hear you.
Sir, okay. Sir, for LZ square, its maximum eigenvalue can be small L square, right?
Correct.
But for capital L square, it is always L into L plus 1, which is greater than L square. But this is a bit counterintuitive for me, because sir, in maximum LZ square means we can think like other two components are 0.
Yeah, but the point is that
how this
the maximum LZ square does not imply that others are
Yes, sir.
0. No?
No, suppose we can consider a case where Lx and Ly are 0.
Okay.
That case, but still
In
it
that
is
case,
less.
no. In that case, your LZ and L are going to be same, right?
Sir.
So your LZ L vector itself is LZ times k cap.
Sir.
So then there is no difference. L square itself is LZ square in that case.
But how we have the eigenvalues for L square and Lz? One and same or what?
Yeah. Sir? So the basically what happens is that so your question is, if I understand your question correctly, when
Yes,
Lx component and Ly component are 0.
Yes, sir.
Correct. Then
Yes, sir.
if Lz alone is non-zero, then in
Yes,
that
sir.
case L square is equal to Lz square, but
Yes,
Lz
sir.
square is m square, but L square is the highest value of m. If you take Lz square is L square, but L square, which is also Lz square, but that
Yes,
is
sir.
L into L plus 1.
Yes, sir. Yes, sir.
Yeah. Okay, that's an interesting question, but such a case does not arise, because see,
Yes,
Lx equal to 0, Ly is equal to 0, Lz is non-zero. Okay,
Yes, sir.
such a case does not arise because that violates uncertainty principle.
Okay, means you are saying two non-commutating operators, Lx, Ly, their
Correct.
commutation will be
So
0
there
in
is an
that.
uncertainty, so you will not be able to make a Lx equal to 0, Ly equal to 0 certainly.
We cannot measure with certainty.
Yes.
That means we can say Lz cannot be aligned along L always.
Yes, definitely they cannot.
Okay, sir. This is nice. I didn't think this way, sir.
Hmm.
But sir, this ground state of hydrogen, that case it is that like that. Sir.
Yeah, ground state of hydrogen correspond to L equal to 0.
0 is an.
Huh?
Sir. Sir. L equal to 0, no?
Yeah, L equal to 0. So L equal to 0 is understood as that the average L is 0. I mean, it's like spherically symmetric. That means it can have all possible directions. When you take an average, it will be 0. For every direction, there is an opposite direction, so it becomes 0.
That L is actually L average, you are saying.
Correct.
Okay, sir. Okay, sir, I got it. Thank you.
Yeah. Okay, so whatever I have written, it is legible, right? You are able to read it and understand.
Yes, sir. We don't feel any difference, sir.
Okay. But this is very convenient for me. I am writing as if I am writing in a notebook.
Is it so, sir?
Yeah, I'm writing, and writing is also easy. At the same time, I am seeing what I am writing. So this is as if I am writing in a notebook. I am able to write.
Sir, is there any lag between your writing and appearing it on the screen, or it is fast enough?
That no, here I don't have any lag, but I don't know if there is any lag between your seeing it and my writing it.
No, it comes instantly only.